missing in the last class? Right. Another sheet on rotational mechanics. Putting together all the concepts that we've learned. That's the objective of the sheet. And reasonably simple sheet. Let's try and get these problems conceptually in place. Rotational motion. Put your acts together. Right, so the first problem of the sheet is about a uniform ladder resting on a smooth floor against a smooth wall. Mass M and length L of the ladder. Let me call it AB. The ladder is AB, making an angle theta with the horizontal at the initial instant. And the ladder is released from rest from this configuration. We want to find the acceleration of the ladder right after release. Okay. See, we are going to first take an elaborate approach to the problem, though not an efficient approach. In the elaborate approach, where it would not require you to have a mental spark to solve the problem, if you do it in the regular physics manner, drawing the free body diagram, writing the equations of motion for translation, equation of motion for rotation, and constraints if required, you'll be all set, right? It's elaborate, lengthy, cumbersome, but it'll give you a recapitulation of some of the concepts that you've already learned. So I'll take to that very elaborate approach first, and then we'll give you a very simple approach to solve the problem. What we are seeking to do is, we seek to find the angular acceleration of the rod right after release. It's released from rest, from this position. All the surfaces that you see here are smooth. Now, let me first draw the free body diagram. Let me draw the free body diagram. What you have is, say, a normal reaction N1 here, a normal reaction N2 here, forces acting on the ladder, and mg. Does it summarize all the forces acting on the ladder? Does it summarize all the forces acting on the ladder? Yes or no? Or are there more forces? Raj? All's good? Okay. Now, the impact of these forces, in as far as translation is concerned, is available at the center of mass. The motion of the center of mass will tell you the impact of these forces. The center of mass, say, has an acceleration a1 downwards because of vertical forces, and has an acceleration a2 leftwards because of all horizontal forces. Yes or no? See, there are horizontal and vertical forces acting on the system. Now, what would be the equation of motion in the vertical direction? Tell me. mg minus n1 is ma1, right? a1. What is the equation of motion in the horizontal direction? N equals, N2 equals ma2, right? N2 equals ma2. Now, N1 and N2 produce a torque about the center of mass. That torque results in an angular acceleration, right? And about the center of mass, therefore, I'm eligible to apply tau equal to I alpha. Torque about the center of mass would be I about the center of mass into angular acceleration alpha. This is theta. If I take the all clockwise torques positive, anti-clockwise torques negative, then N1 about the center of mass will produce a clockwise torque, N2 will produce an anti-clockwise torque about the center of mass. Yes or no? Okay. What's the clockwise torque of N1 about the center of mass? N1 into this perpendicular distance. This is L by 2 cos theta, isn't it? This length is L by 2. So this length is going to be L by 2 cos theta. So N1 into L by 2 cos theta. Now, anti-clockwise torque of N2 about the center of mass is going to be what? N2 into L by 2 sine theta. This length is L2, so this length is going to be L by 2 sine theta. So minus N2 into L by 2 sine theta. Right? That's a net clockwise torque about the center of mass. And this results in a clockwise angular acceleration alpha. That is I about the center of mass into angular acceleration alpha. Right? What is I about the center of mass for about this? 1/12 ml square into angular acceleration alpha. Now, have we done enough? How many unknowns are there? N1, A1, N2, A2, 4, N1, 5. 5 unknowns, 3 equations. Inadequate. We have consumed Newton's laws. We have consumed the equation for rotation, etc. We can't do. Now, what is pending is constraint. Constraint. Physically, what constraint is pending? No. Don't talk of mathematics first. Talk of the physical constraint. Do these equations reflect that the net acceleration of A1 will be downwards only and the net acceleration of B would be leftwards only? Do these equations reflect in any manner the accelerations of the ends? It doesn't, right? So I have to put together those physical aspects in place in the form of equations. The constraint pertaining to A1, the constraint pertaining to A and pertaining to B. Now, look at the rod. This is the rod. Center of mass A1, A2, right? And angular acceleration alpha. These things, acceleration of the center of mass and angular acceleration of the rod, will tell you the complete story of the rod, right? Now, if I have to designate, this angle is theta. Now, if I have to designate the acceleration of the end A, how would I compute the acceleration of the end A? Can you tell me? I would superimpose pure translation with pure rotation. That's what I'm going to do, right? Because of pure translation, A has an acceleration A1 downwards, common with the center of mass, and A2 leftwards, again common with the center of mass, right? Now, imagine the rod to be in a state of pure rotation about the center of mass with angular acceleration alpha, right? See, if this were to be in a state of pure rotation about the center of mass with angular acceleration alpha, this length is L by 2, then it will have a tangential acceleration which would be L by 2 alpha. Yes or no? In pure rotation, angular acceleration about the center is L alpha, R in this case is L by 2. So, this will now have, because of pure rotation, it will have an acceleration which would be L by 2 alpha, Very clearly, this angle is theta. Now, the net acceleration of A is the resultant of A1, A2 and L by 2 alpha. L by 2 alpha will be perpendicular to the rod, tangential acceleration, right? Yes or no? Right? And A cannot have a vertical acceleration. That means the vertical component of all these forces put together must be 0. That means L by 2 alpha cos theta must be equal to A1. L by 2 alpha cos theta must be equal to A1. Yes or no? Right? Fourth. Now, similarly, let me look at the end B. Let me look at the end B. The end B will have an acceleration A1 downwards, common with the center of mass. A2 leftwards, center of mass. And imagine it to be in a state of pure rotation about the center of mass O. It's going to have a perpendicular acceleration, right? Like this. L by 2 alpha. What do you say? The resultant of A2, A1 and this L alpha by 2 would be the net acceleration of B, this end B, which has to be vertical. That means, look, this angle is theta, this angle is theta. Now, the acceleration of B horizontally must be 0 because, I'm sorry, I have labeled them differently. Call this B. Let me be consistent. This is B and this is A. This is A. Okay. So the acceleration of A has to be purely vertical. That means its horizontal acceleration must be 0. That means, can I say A2 must be L alpha by 2 sine theta? Acceleration in this direction, L alpha by 2 sine theta must be equal to A2, so that the net acceleration horizontally is 0, right? So L alpha by 2 sine theta must be equal to A2, right? So now 5 equations, 5 unknowns, and you can make merry with them, right? It was important to communicate this elaborate approach, but this is not what you should have typically done once you grow up to rotational mechanics. You can economize the solution. We'll economize the solution now, right? But I hope all of you understand the physics involved. Basic equation of translation, drawing the free body diagram, from there looking at equation of translation, equation of rotation, which manifests in the center of mass, the angular acceleration applied obtained by using tau equal to I alpha, and the two constraint entities. Acceleration of B horizontal, acceleration of A vertical, all put together we are in shape. Clear? Now, let me give you a simpler way of solving this problem. Let me give you a simpler way of solving this problem. Can I wipe this off? Give me a few seconds, you'll know. See, if you recall, in general rigid body motion, there is a point called the instantaneous center, right? How do you obtain the instantaneous center? If this point has a velocity v1 like this, and say this point has a velocity v2 like this, then to obtain the instantaneous center, you draw a perpendicular to v1, you draw a perpendicular to v2, and the point where these two lines intersect would be the instantaneous center IC. Yes or no? That's going to be the instantaneous center IC. And tau equal to I alpha can be applied about the instantaneous center as well. There are only two legal positions about which you could apply tau equal to I alpha: the center of mass and the instantaneous center, right? Now, See, at all times, for this, this angle is theta. B is constrained to move this way. So the velocity of B would always be directed along this. The velocity of A will always be directed along this. Drop a perpendicular to the velocity of B, which would be like this. Drop a perpendicular to the velocity of A, which would be like this, right? And this would be the instantaneous center of the rigid rod. This would be the instantaneous center of the rigid rod, yes or no? Now, forces. Say N1 like this, N2 like this, the two normal reactions, and mg this way. And I have the luxury of applying tau equal to I alpha about the instantaneous center. And if I did that, then in one shot, I would get rid of N1, because N1 will produce no torque about the instantaneous center. N2, its line of action passes through the instantaneous center, will not produce torque about the instantaneous center. And the only thing that I would have to deal with, the torque of mg about the instantaneous center. And question is, how is it that I'm able to solve the problem without using any constraints? The constraints are built, because in locating the instantaneous center, I have taken the velocity of B like this, velocity of A like this. That means in order to locate the instantaneous center, the direction of motion of A and B have been built into the situation, and therefore it would require no extra mathematical treatment to express the same. Right? Right? So good for us. Now, it's just about taking torque of mg about the instantaneous center, torque of mg about the instantaneous center, right? The torque of mg about the instantaneous center. See, this length is L by 2. This is L by 2 cos theta. Right? Mg into this length would be the torque. And clockwise, mg into this length. That means mg into L by 2 cos theta is the clockwise torque about the instantaneous center. That must be I about the instantaneous center into angular acceleration alpha. Right? The only thing that we need to then handle is the moment of inertia about the instantaneous center. I'm going to use parallel axis theorem, right? Hey, what would this length be? If this is the center of mass O, what would this length be? What would this length be? What would this length be? L by 2, yaar. Very simply, this is going to be L by 2. This is half of this diagonal, and the two diagonals are equal, isn't it? So this is half of this diagonal, which is the same as half of this diagonal, yes or no? So this length is L by 2. This length is L by 2. Or the other way you can look at it is, with O as the center and L by 2, this or this as the radius. If you draw a circle, then it will pass through this, because this is angle in a semicircle, right angle. And then each of these would be radii of the same circle and equal to L by 2. Right? So then, I about the instantaneous center obtained from parallel axis theorem is going to be I about the center of mass, which is 1/12 ml squared plus m into this square, L square by 4. Which is 1/3 ml squared. So plug in I about the instantaneous center as 1/3 ml squared and obtain alpha right away from this equation. One line solution. That's all that it means. Right? All the physicality has been incorporated in it. Clear? Obviously, because they produce non-zero torque about the center of mass. right? Okay. Here we have a square plate in 3 possible configurations. This is a square plate hanging vertically, length C, width C by 2, and one way it is being held is this 2 pins A and B. The other mode of holding it was the following. These are 2 wires. A and B. Same length C and C by 2. These are 2 wires, or threads, so to say. Bless you. These are 2 threads. And the third mode was the following. Two identical springs. Two identical springs. Now, what is done is, in each of these cases, B is released. The pin here is released. This wire is snapped here. This spring is snapped here. I want to be able to find the angular acceleration of the square lamina, of the, not a square, a rectangular lamina. I want to be able to find the angular acceleration right after release in each of the 3 cases. Right? Okay. Now, can I remove the clutter from here and just deal with this? See, when I remove this pin, what transpires? When I remove this pin, what kind of a motion would be exhibited by the lamina? Pure rotation about A. It's going to exhibit pure rotation about A. Yes or no? And that makes life very easy, because if it is pure rotation about A, what are the forces? There is mg, and at this pin there is a force, but I don't have to bother about the force at A, because if I seek to take torque about A, then those forces will produce no torque about A. So the only force which is relevant in terms of producing torque about A is mg. So I take torque about A, equal to I about A into alpha, right? That's the only thing. It's going to exhibit pure rotation about A. The rigid body would get into a state of pure rotation about A, right? Now, so this length was C. This would be C by 2, right? What's the torque about A? What's the net torque about A? mg into C by 2. That must be equal to I about A into angular acceleration alpha, right? That must be equal to I about A into angular acceleration alpha. I need to therefore only compute I about A for the rectangular lamina. Now, in a rectangular lamina, suppose this length is A, this length is B, then I about this axis, an axis passing through the center of mass, an axis passing through the center of mass, and perpendicular to the lamina is 1/12 m a squared plus b squared. I about the center of mass axis. I about the center of mass axis is 1/12 m a square plus b square. That's I about this axis. So if I have to find I about this, and suppose this length is x, then I about this axis using parallel axis theorem would be I about cm plus mx squared, where x would be half the diagonal. X is what? Half root a square plus b squared, right? So I about a is going to be I about cm plus mx squared using parallel axis theorem. X is half the diagonal, half of root a square plus b squared. Clear? This is what we need to take care of. All right, so let's apply the same to this problem. Can I remove this? So I about the center of mass in this case is 1/12 m c squared plus c squared by 4. Right? This x is half the diagonal, right? X is what? Root half of root c squared plus c squared by 4. That's x, which is 1/4 root 5c. 1/4 root 5c. That's x. And therefore, I about a could be computed. What would be I about a? I about a would be I about an axis passing through the center of mass plus m into x squared, which is 5c squared by 16. So this is 48, 5/48 mc squared plus 5/16 mc squared, which is 20/48 mc squared. That's I about this axis. That's I about this axis, which you can plug into this and obtain the value of alpha. Right? All's good? Now what's the next part to the same problem? Not just alpha. We need to find the acceleration of the center of mass right after release. Alpha we have found. We also want to find the acceleration of the center of mass right after release. Right? How do we do that? So alpha is known. We'll assume that alpha has been computed using this equation. Can I remove this? See, what is the center of mass doing? This is A. The center of mass is moving in a circle of radius x that we've already computed, right? Centered at A. So it will move in this circle. With angular acceleration alpha, the center of mass will move in this circle of radius x centered at A with angular acceleration alpha. It will therefore have a tangential acceleration like this, which is going to be x alpha. X alpha. That's going to be the acceleration of the center of mass. X alpha, clear? So the acceleration of the center of mass is going to be like this. ACM is x alpha. X has been known, alpha has been known. And if you want to resolve it, say this was the y direction, this was the x direction, and if you choose to resolve this, say this was the vertical direction, say this angle was theta, then this is c by 2, so tan theta is 2. This tan theta would be 2, isn't it? C divided by C by 2, that's 2. And if this is theta, this is 90 minus theta, so this is theta. So the acceleration of the center of mass vector is going to be minus ACM cos theta I cap minus ACM sin theta j cap. Vectorially. Yes or no? Where if tan theta is 2, sin theta would be 2 by root 5, right? Cos theta would be 1 by root 5, which you can plug into this. ACM has been computed using x alpha, and you can obtain the acceleration vector. Make sense to all of you? Let's look at the next part of the problem, where it's suspended using threads. The same lamina suspended using threads. But all's clear, right? So the second situation is as follows. This is the lamina, and these are the two threads. And the second thread is suddenly snapped. This one at B is suddenly snapped. And I want to solve the problem afresh. See, when the whole thing was in place, there was mg like this, there was t and t from symmetry like this, and 2t was equal to mg earlier. Before B was snapped, 2t was mg. But now, if I suddenly snap B, so t turns out to be mg by 2. Now if I snap B, what do you think would happen to t? Will it remain the same or change? It will change. Why? Because because the string is an impulsive element. So tension would respond instantly because of the change in dynamics. So t will no longer remain mg by 2. T will become something else. Let's say t becomes some new t. Right? This then summarizes all the forces acting, right? This summarizes all the forces acting on the... Now, what kind of motion will it exhibit? No, it cannot be. General rigid body motion. It will get into general rigid body motion. It will develop ACM and it will also develop alpha. Simultaneously, it will begin to swivel, and the center of mass will also begin to have a downward acceleration, right? General rigid body motion is what transpires here. The center of mass develops an acceleration ACM, and alpha is the angular acceleration developed by the rod. Now, what is the equation of motion for translation? equal to MACM, right? mg minus t equals MACM. Now, about what point will I take tau equal to I alpha? Tau equal to I alpha, about what point would I apply? It will be a sin to apply it about A. A is not the pivot. The only point about which I am eligible to apply tau equal to I alpha here is the center of mass. A is not the instantaneous center. A is not a pivot. Earlier, in the earlier case, A was a pivot about which it was in a state of pure rotation. Now it's not in a state of pure rotation about A. So the only legal position about which I should be applying tau equal to I alpha is the center of mass. So this length is c by 2. mg produces no torque about the center of mass. So T into c by 2 is the clockwise torque producing a clockwise alpha, right? T into c by 2 must be I about the center of mass, which is 1/12 m c squared plus c squared by 4 into angular acceleration alpha. Yes or no? Torque about the center of mass, T into c by 2 would be I about the center of mass, which is this 1/12 m a square plus b squared for a rectangular lamp into angular acceleration alpha. Right? How many unknowns are there? T, ACM and alpha. T, ACM and alpha. And I'm done with these equations or the types. I still need a filler equation to take care of a filler entity here. See, all points on this rigid body would be in a state of generalized motion, and A would have an issue. A is connected to a string like this, right? If I had to calculate the acceleration of A, how do I do that? I will superimpose pure translation with pure rotation. A, because of pure translation, it will have ACM like this, which it will share with the center of mass, right? Imagine it to be in a state of pure rotation about the center of mass. Imagine it to be in a state of pure rotation about the center of mass. Suppose this length is x, distance between A and the center of mass. Then it will have an acceleration perpendicular to this diagonal equal to x alpha like this. Yes or no? Say this angle is theta, which we have computed. Tan theta is 2. Now, this is a string, vertical. Can it have a vertical acceleration? A can have a leftward, rightward acceleration, but can it have a vertical acceleration? No. That's a string constraint. So vertical acceleration of A must be 0. That's a physical constraint for the problem. Vertical acceleration of A must be 0. And the net acceleration of A is x alpha perpendicular to the diagonal and ACM like this. This is theta. This is theta. Yes or no? So x alpha sine theta must be ACM. X alpha sine theta must be equal to ACM. Which one? This is theta. So this is 90 minus theta. So this is theta. No? This is perpendicular. What? No? We learn a lot of things out of these three situations. A lot of things, get packaged in one place while solving these three situations. Let's look at the the other thing, the acceleration of the center of mass. Okay, now, how do I find the acceleration of the center of mass in this case? Obviously, I can eliminate T and alpha from this and find ACM. It's going to be purely vertical. Acceleration of the center of mass can be easily found. Right? Clear? Okay. Last part of the problem, which is a spring. Can I wipe this off? So the last part of the problem is these two springs mg. Now if the spring force is F, both springs will elongate to balance the weight. So 2F would be mg. Before I snap B, F therefore would be mg by 2, right? Now if I snap this spring, what happens to the force in this spring? Yes, it will remain the same because the spring is not impulsive. Is not impulsive. See, this is the distinction I want you to understand. You know, for the same situation, we looked at a spring and a string, so as to, you know, cast out this difference. So F will remain the same even after B is snapped because the spring is non-impulsive in character. Right? Now, F is known therefore, good for us. So this situation is simpler than the string situation where T was not known to us, right? So, and there is nothing about A having a vertical acceleration in this case or not having a vertical acceleration, right? So I can take torque about the center of mass. This is C by 2. So F, which is known, into C by 2 is going to be I about the center of mass into angular acceleration alpha. Right? So alpha ICM we have already computed. Alpha can be obtained. And what about the acceleration of the center of mass? mg minus mg by 2 divided by m. mg minus mg by 2 divided by m, that makes it g by 2 downwards. That's the acceleration of the center of mass in this case. No? Not sure. What is the net force acting? mg downwards, spring force mg by 2 upwards. ACM was the acceleration of the center of mass, so can I say mg minus mg by 2 is MACM? So ACM is g by 2. Got it. Yes, of course. Problem number 3 is a uniform disk, say mass m and radius r, which you can pretend that you know, right? Rolling, rolls without sliding, pure rolling, is in a state of pure rolling on a fixed horizontal surface. We want to find the ratio of the kinetic energy of the upper half to the kinetic energy of the total disk. Say if this was the center of mass O, and this is V, and this was omega, we want to find the total kinetic energy of this, or rather kinetic energy of the upper half of the disk to the total kinetic energy of this. Now total kinetic energy is no big deal. The total kinetic energy is half mv squared plus half ICM omega squared, right? Or you could have taken half of I about the instantaneous center into omega squared, right? Because this point of contact is also the instantaneous center in pure rolling, because it has zero velocity. There is no relative motion between this point and this surface, so this could be looked upon as the instantaneous center. Its velocity zero. Velocity of point of contact is zero. That's why it's the instantaneous center. No, why? When you can figure out that the velocity is 0, then why do you want to draw a perpendicular, yaar? Right? So this is half mv squared plus half ICM. ICM is half mr squared for a disk. And omega is v by r. Because it's in a state of pure rolling, v is r omega in pure rolling. So this will give you the total kinetic energy in terms of v. Right? Now, let me obtain the kinetic energy of the upper half. Let me obtain the kinetic energy of the upper half of the disk. Can I wipe this off? Wipe it off? Okay. Kinetic energy of the upper half. Let's see how to obtain that. See, in principle, this was the upper half of the disk, which is now a semicircular disk, The upper half by itself has its own center of mass O1. O1 is the center of mass of the upper half. I'm looking at the upper half in isolation, right? Now, if this point O1, which is the center of mass of the upper half, had a velocity v1, this is angular velocity omega, then this is the center of mass of the upper half. So the kinetic energy of the upper half, is going to be half of m v1 squared, velocity of the center of mass, plus half of I about O1 into omega squared, half of ICM omega squared, half of m VCM squared, plus half of I about O1 into omega squared. Yes or no? That's how you'll compute the kinetic energy of the upper half. So what's the task? The task is to find V1 and IO1 for the upper half. Moment of inertia of the upper half about its own center of mass. These are the two things essentially then. Right? Now, first things first. Let me locate the center of mass of the disk. In a semicircular disk, the center of mass is 4r by 3 pi from O, right? So this is 4r by 3 pi. The mother disk, which is the full disk, was like this, and O had a velocity v, the center of mass, and it had an angular velocity omega. Then from superimposition, the velocity of O1 would be v1 would be v because of pure translation, and then imagine it to be in a state of pure rotation about O. It's going to be this length into omega, 4r by 3 pi into omega. Yes or no? Where this r omega is v. This r omega is v. Yes or no? V is r omega. So this is v plus 4 by 3 pi into v, which is 7 v by 3 pi. V1 known? V1 known, so no issues. This part taken care of. Now the second aspect. Omega can be written as v by r. Omega is v by r. So I just need to find the moment of inertia of the semicircular disk about O1. This is all that I need to do. Yes or no? So can I remove the clutter from here? See, tell me the following. This is O1, the center of mass of the upper half. This is O2, the center of mass of the lower half. Right? This is O. Now, the moment of inertia of the upper half about O plus moment of inertia of the lower half about O will be the moment of inertia of the entire disk about O. Yes or no? So if the moment of inertia of the upper half about O is I naught, then the moment of inertia of the lower half about O will also be I naught. And 2 I naught 2 I naught must be moment of inertia of this whole thing about O, which is half mr squared. So I naught would be 1/4 mr squared. I naught would be 1/4 mr squared. Clear? Now, so I know the moment of inertia of the upper half about O. I know the moment of inertia of the upper half about O. Now from parallel axis theorem, can I say I about O for the upper half? I'll apply parallel axis theorem. I about O would be I about its Cm, that is I about O1 plus m into 4r by 3 pi squared. Can I say this? I about O from parallel axis theorem would be I about its own center of mass O1 plus m into 4r by 3 squared. So I about O we have computed. So I about O1 can be obtained from this equation, which you can plug into this, write omega as V by R, and you would know the kinetic energy of the upper half alone. And then of course you can divide and obtain the ratio. Right? So we have a structure like this. This is y equal to x squared, the upper bound. This is y equal to minus x squared, the lower bound. This is x equal to a. Right? We need to find the moment of inertia of this arrangement, this lamina, about the x-axis. Right? About the x-axis is what we need to do. It's given that rho is the mass per unit area of this lamina. Mass per unit area of this lamina. That's given. Now what I could do is, in principle, let me take the upper half, for example, and break the upper half into smaller rods of this kind. And the moment of inertia of this rod about this end would be 1/3 ml squared, m into length of the, right? This is what I can do, and then sum up the moments of inertia of all such rods starting from x equal to 0 to x equal to a. That is what we would do in principle, right? So now suppose I selected this rod at x and its y. This y would be x squared. This y would be x squared. This is almost rectangular, and say this is of thickness dx. This is of thickness dx. So the moment of inertia of this about the x-axis is going to be 1/3 mass of this. What's the area of this? Y equal to x squared. Y into dx would be the area of this. That means x squared into dx is the area of this. Right? Into rho will give me the mass of this. This is mass, rho is the mass per unit area. And this area is dx into this length, x squared. Dx into x squared, right? 1/3 m l squared. This x squared is the length of the disk, of the rod. So x squared whole squared, ml squared. Whole squared. That's the moment of inertia contribution made by this shaded rod about the x-axis, right? The total moment of inertia is going to be, of the upper half, is going to be sum of all of this, where x runs from 0 to a, that's the upper half, and the lower half will make an equal contribution. So this will be the total moment of inertia about the x-axis of this arrangement. This is easy to compute. X power 4 into x power 6, so x power 7 by 7, so a power 7 by 7, etc. So 2 by 21, etc. M L squared? L is x squared, isn't it? So 1/3 m L is x squared, L squared, right? Have you looked at the fifth one? Can I wipe this off? So fifth one is a rod of this kind, a rod AB. This angle is given to be 60 degrees and this surface is very rough. Rough enough to prevent A from sliding on the ground. This is rough enough to prevent A from sliding on the ground, right? The length of the rod is L and this angle beta is given to be 60 degrees. And this starts from rest. We want to be able to find, number one, the angular acceleration of the rod right after release, the normal reaction and friction at A, and the minimum value of mu, coefficient of friction between the rod and the ground, so that this could happen. What's the minimum mu for which A will not slide on the ground, right? All mu's higher than that would cause the motion to be compatible with A not sliding on the ground, right? Okay. So first of all, if A does not slide on the ground, what is the nature of the motion? Pure rotation about A. Pure rotation about A, right? What are the forces? There is, A has a tendency to slide leftwards, so friction would act rightwards. What would be the nature of this frictional force? Static. It will be less than or equal to mu n, right? It's static in character. And then there is going to be normal reaction n upwards and weight downwards. Right? So to find the angular acceleration alpha, what would I do? Tau equal to I alpha about A. Tau equal to I alpha about one end of the rod is what I'm going to do, right? What is torque about A? F and N produce no torque about A. mg into this length is the torque about A. That will be the clockwise torque producing clockwise alpha. So mg into L by 2 cos beta. mg into L by 2 cos beta is I about A. What's I about A? 1/3 ml squared into angular acceleration alpha. So alpha is known from these considerations. Cos 60 is half and so on and so forth. Right? So what does this turn out to be? Alpha equals 3g by 4l. 3g by 4l radians per second squared is the angular acceleration. Right? Now, center of mass, right? It will move in a circle of radius L by 2 centered at A. So the center of mass will have an acceleration which is perpendicular to the rod, L alpha, L by 2 alpha. ACM perpendicular to the rod is going to be L by 2 alpha. Perpendicular to the rod, right? It will move in a circle of radius L by 2 centered at A. So tangential acceleration R alpha, L alpha is 3g by 4, so this will be 3g by 8, isn't it? L alpha is 3g by 4, so L alpha by 2 is going to be 3g by 8 meters per second squared, right? That's the acceleration. Now, this is 60 degrees. Could be resolved. This is 60 degrees. In the horizontal and vertical direction, this ACM could be resolved in the horizontal and vertical direction, right? In the horizontal direction, that is AX, it's going to be ACM sine 60 degrees. ACM sine 60 degrees means 3g by 8 into sine 60 degrees means root 3 by 2. That's ax. And this is ay. Ay is what? ACM cos 60 degrees. That means ay is going to be 3g by 8 into half. That means 3g by 16 is the vertical acceleration, ACM cos 60 degrees. Right? So you know ax and ay. Okay, you already know the effect, so you can find the cause. F is instrumental in producing ax. mg minus n is instrumental in producing ay. Right? So F is known. What is F? F must be max. So F is known, ax is known, right? And mg minus n. Mg minus n is may. Ay is known. So n is known. N is known, yes or no? So this is may. That means 3 mg by 16. So n then becomes 13 mg by 16. Is n 13 mg by 16? Now F is always less than or equal to mu times n. Mu times n. So mu will be greater than or equal to max divided by this. So the minimum mu will be max divided by this. Ax is known. So that will give me the minimum mu that will make the motion compatible with the given conditions. Right? So there is a 6 kg carriage. There is a 6 kg carriage and is supported as shown by 2 uniform discs, 4 kg each. And the radius of each of these discs is given to be 75 mm. Knowing that the carriage is initially at rest, determine the velocity of the carriage 2.5 seconds after the 10 Newton force has been applied. This 10 Newton force is applied and we want to be able to determine the velocity of the carriage 2.5 seconds after application of this force. That means if I can find the acceleration of the carriage, then I am taken care of, isn't it? I just need to find the acceleration of the carriage. And it's also given that the disc rolls without slipping. The 2 discs, there is no slipping anywhere. See, there are 2 vulnerable locations for slipping. One is between the disc and the ground, the other one is between the disc and the carriage. We'll assume that there is no slipping anywhere at all. Now, let me take you back a little bit. One thing, if this body rolls on the surface, and if v is the velocity of the center of mass, and omega is the angular velocity of this, then for rolling without slipping, the velocity of the point of contact is 0. Velocity of the point of contact is obtained by VCM because of pure translation. Imagine it to be in a state of pure rotation, r omega like this. So VCM equal to r omega will cause the velocity of the point of contact to be 0, and it will be in a state of pure rolling. So VCM equal to r omega is the condition required towards pure rolling. Now, not only that, if this is a fixed horizontal surface, and if this is VCM, this is omega, then VCM equal to r omega, and now if VCM is changing with time, omega must also change with time, so that from instant to instant, this condition remains validated and rolling persists. So now if I differentiate both sides with respect to time, then this will become ACM equals r alpha, right? ACM equals r d omega dt, which is alpha. Naturally, if I look at the velocity of the topmost point, it will be VCM because of pure the center of mass translation, pure translation. Imagine it to be in a state of pure rotation about the center of mass. It will have r omega like this. That means this will be twice VCM, because r omega is VCM in pure rolling. That means the velocity of the topmost point is twice the velocity of the center of mass. Similarly, the acceleration of the topmost point will be twice the acceleration of the center of mass. Right? Okay. So just in case these facts were forgotten, so acceleration of the topmost point is twice the acceleration of the center of mass. Okay, can I remove the clutter from you? Now, if I look at each of these disks, we will assume from symmetry considerations that each of these disks would be in identical states of motion, would experience the same force, and so on and so forth. So if I look at any one of these disks, any one of these disks, if A is the acceleration of the disk, right? Alpha is the angular acceleration of the disk. Then A must be equal to R alpha for sure, right? And the topmost point of the disk will have an acceleration A plus R alpha, which would be 2A. The acceleration of the topmost point would be 2A, twice the acceleration of the disk, right? Okay. Now, if A is the acceleration of the disk, then the topmost point does not slide with respect to the carriage. Therefore, if the topmost point has an acceleration 2A, the acceleration of the carriage must also be 2A. That means if the acceleration of the center of mass of each of these disks is A, then the acceleration of the carriage must be 2A. That's guaranteed. That means if this is A, the acceleration of the carriage must be 2A for sure. Yes or no? No, it's the condition for no slipping between A and the carriage. Right? Now, free body diagram of the disk. What are the forces acting on the? There is mg and there is normal reaction, which we will not unnecessarily depict. Then for the disk, there is, say, friction F acting between, static friction between A and the carriage, because there is no slipping. Nature of friction must be static. Let's say the carriage exerts on the disk a frictional force, static friction F like this. Then there is friction between the ground and the disk. Now you may not necessarily know the direction. You can take arbitrary directions. Say F1 is the frictional force between the disk and the ground. And the net effect of these is an acceleration A and an angular acceleration alpha. And do you realize that this point of contact has zero velocity at every instant? So you could imagine this to be the instantaneous center for the disk. The point of contact has zero velocity at all times. So this could be imagined to be the instantaneous center at all times. Now, see, can I obtain alpha? How can I obtain alpha? Either I can take torque about the center of mass. What would be the equation for torque about the center of mass? F, say R is the radius of the disk. So F into R anticlockwise minus F1 into R clockwise. That must be I about the center of mass, which is half mr squared into alpha. M is the mass of the disk. Yes or no? But in writing this, there is F1, which is unnecessarily sticking its head out. Right? So is there a way, bless you, I could obtain alpha or obtain a more convenient equation in which F1 doesn't appear? Yes, take torque about the instantaneous center, then there would be no occurrence of F1, which means, so this, even though this is right, it is not economically viable, right? So I would rather take torque about the instantaneous center, which is the point of contact. So what is it that we have? F into 2R is the torque about the point of contact. That's the net torque, anticlockwise. That must be I about the point of contact, which is what? 3 by 2 mr squared. If small m is the mass of the disk, then 3 by 2 mr squared is the I about the point of contact. So 3 by 2 mr squared into angular acceleration alpha. That way F1 doesn't feature in the equation. I don't want F1 to unnecessarily feature in the equation, right? F into 2r is 3 by 2 mr squared alpha. Now, this and this would get cancelled. But since it's rolling without slipping, A must be equal to R alpha. See, I want to eliminate alpha. I just want to have A, because if I know the acceleration of the disk, then 2A would be the acceleration of the carriage. So I don't want alpha to be unnecessarily poking in my equations, right? So what I do is I write this R alpha as A. That's the condition for rolling without slipping. So this would be 3 by 2 MA. That's 2F. Right? F then is 3 by 4 MA. M is the mass of the carriage. That means M is 4 kg. So this will become 3A. That's frictional force, static friction between the disk and the carriage in terms of the acceleration of the disk. Yes or no? Clear? And I don't have to repeat for the second disk because the same equations will hold good for the second disk. Right. Now let me get to the carriage side of the story. Let me look at the carriage side of the story. So far so good, right? The carriage, okay, what are the forces other than normal reaction and mg? What are the forces acting on the carriage? F, which is 10 newtons, right? F, which is 10 newtons, and tell me 2F, because if the carriage exerts on this disk, F to the left, this disk will exert on the carriage, F to the right, and each of these disks would exert on the carriage, small f to the right. So there is 2F to the right. And what is the net effect of this? If A is the acceleration of this, then 2A will be the acceleration of the carriage. We then have F, which is 10, minus 2F. 2F. 2F would be 6A. 2F would be 6A. 6A must be mass of the carriage, which is 6, into acceleration of the carriage, which is 2A. Yes or no? That's equation of motion applied to the carriage. 18A is 10. A therefore would be 5 by 9 meters per second square. Right? So what would be the acceleration of the carriage? 10 by 9 meters per second square would be the acceleration of the carriage. Yes or no? What would be the velocity of the carriage? How many seconds later? 2.5 seconds later. Initial velocity is 0. Acceleration of the carriage is 10 by 9 into time 2.5. So 25 by 9 meters per second would be the velocity of the carriage. All's good? V is u plus 80. A is 10 by 9 for the carriage into t, which is 2.5. It's a case of constant acceleration, so I could deploy V equal to u plus 80 for the carriage. Right? Let's look at the next problem. How many of you could do it, right? Okay, 1, 2. Okay. See, again, you know, very illustrative in character. Again, very illustrative in character. Umpteen things illustrated in one single example, right? So there is a rod AB. This is a rod AB. And we want to be able to apply a force P on the rod somewhere. This rod is of length 0.9 meters, resting on a smooth horizontal surface. Length L is 0.9 meters for the rod. We want to find the position P where a force of magnitude 2.7 newtons be applied. Such that the acceleration of the, oh, this is A and B ulta. Okay, so this is B, this is A. such that the acceleration of B is 0. We want the net acceleration of B to be 0. I want to find the location where P must be applied so that acceleration of B is 0. Right? Okay. See, let me locate P with respect to the center of mass of the rod. See, this is the center of mass of the rod, and P is applied x units from the center of mass. X units from the center of mass. I need to find x such that acceleration of B is 0. This is what we want to be able to do. Okay. First of all, how does this P manifest itself in terms of the center of mass? P must be mass into acceleration of the center of mass. Yes or no? So if the acceleration of the center of mass is A, then can I say that P must be m into A? Now, what else does this P do to the rod? It produces an alpha. Because about the center of mass, there is a torque P into x acting. That must be I about the center of mass into alpha. Right? So the torque equation, P into x, the torque about the center of mass, must be I about the center of mass, which is 1/12 ml squared, into angular acceleration alpha 2. Yes or no? Now, okay. So in terms of A and alpha, if I have to find the acceleration of B, because of pure translation, B would have an acceleration A to the right. Imagine it to be in a state of pure rotation about the center of mass. It will have an acceleration L by 2 alpha to the left. So what would be the net acceleration of B? A minus L alpha by 2, which must be 0. Right? Acceleration of B equal to 0 means A must be equal to L alpha by 2. Right? So this can be written as 1/12 ml into L alpha. L alpha is 2A. See, 1/12 ml into L alpha. L alpha I have written as 2A here. Right? That's P into x. And in order to find x, what would I do? I divide this by this. A will get cancelled. L is known to me. M will get cancelled. And I'll have the value of x. If I divide this by this, I'll get the value of x. Right? Sounds fair? This is a rod of length L, and these are two springs. These are two springs. This is a slender rod of length L and mass m. This is spring 1, this is spring 2, and this is given to be 30 degrees. This is given to be 30 degrees. If now spring 2 suddenly breaks, I want to find the angular acceleration of the bar, I want to find the acceleration of A, and I want to find the acceleration of B. This is what I want to be able to do. Right? Okay. See, if F is the force in each spring, then do you realize that the vertical component of these forces will balance the weight initially when 2 was not snapped? So F sine 30 degrees plus F sine 30 degrees must be equal to mg. That means initially 2F sine 30 degrees must be equal to mg. So that gives me F equal to mg. That's the force in each of the springs. F is mg. Now, simple, isn't it? Horizontal component of these forces will cancel off, producing no horizontal acceleration of the center of mass. Okay, now if this spring is snapped, now if I snap this spring, what will happen to this? Why? Non-impulsive. Spring is non-impulsive. So this spring force will not change, which is such a blessing for us. Right? This F could now be resolved as F cos 30 degrees like this. That means mg cos 30 degrees, mg root 3 by 2. F cos 30 degrees, isn't it? F is mg, so mg cos 30 degrees. And it could be resolved as F sin 30 degrees vertically, which is mg by 2. Right? And then there is AB. There is mg acting like this, mg root 3 by 2, mg sin 30 degrees. Right? mg root 3 by 2, mg cos 30 degrees, mg sin 30 degrees. This is the summary of all the forces acting on the rod right after 2 is snapped. Now, what would it result in? First of all, how do you find angular acceleration? Will you take torque about A or B or center of mass? Center of mass. A is not the instantaneous center. So, we'll take torque about the center of mass. What's the torque of mg root 3 by 2 about the center of mass? 0, because its line of action passes through the center of mass. What's the torque of mg about the center of mass? 0. So, what's the only non-zero torque about the center of mass? mg by 2 into L by 2. mg by 2 into L by 2 will produce a clockwise torque and therefore a clockwise alpha, right? So, mg by 2 into this length, which is L by 2, is the torque about the center of mass, clockwise torque about the center of mass. That must be equal to I about the center of mass, which is 1/12 ml squared into alpha, right? So, we get L alpha equals 3g, alpha equals 3g by L, alpha equals 3g by L, yes or no? So, angular acceleration known to us. Okay. Let me note it down here. L. Now, let me remove all of this, right? Can I remove the clutter from here? Okay. How do I find the acceleration of the center of mass? Will the center of mass move down or will have a rightward acceleration also? Yes. Because of this, there would be a rightward acceleration of the center of mass. Combination of mg and mg by 2 will give it a downward acceleration. Okay. So, suppose let me call this the y direction. Let me call this the x direction. All right. What's the acceleration of the center of mass in the x direction? The force in the x direction is mg root 3 by 2 divided by m. So, g root 3 by 2 in the x direction. What's the acceleration of the center of mass in the y direction? mg minus mg by 2 divided by m. That makes it g by 2 is the acceleration of the center of mass in the y direction. Okay. So, now I have knowledge of alpha and ACM both. Given this, I want to be able to find the accelerations of points A and B. So far so good, right? Can I remove the unnecessary stuff from there? See, for the rod, there is acceleration in the y direction, which is g by 2 for the center of mass, the acceleration in the x direction, which is g root 3 by 2. These are points A and B. And then there is angular acceleration alpha, which we have computed as 3g by L, right? Now look at A. Because of pure translation, it will share a common acceleration with the center of mass. So, it will have an AX like this and it will have an AY like this. Yes or no? Imagine it to be in a state of pure rotation about the center of mass. It will have an acceleration L alpha by 2, R alpha, R is L by 2 into alpha like this. Imagine it to be in a state of pure rotation about the center of mass with angular acceleration alpha. It will have r alpha like this, where r is L by 2. Yes or no? So L alpha by 2, of course. L alpha is 3g. So 3g by 2. This is 3g by 2. So ax and ay are known. What's the acceleration of A? Acceleration vector of A, assuming this is the x direction, this is the y direction. The acceleration vector of A is going to be ay minus 3g by 2 I cap j cap, right, plus ax I cap. Ax and ay are known. Ax and ay we have computed. This would be the acceleration vector of the point A. Now similarly for the point B, there is going to be an ax like this, and there is going to be an ay like this, right? Imagine it to be in a state of pure rotation about the center of mass. It will have a tangential acceleration L by 2 alpha. Yes or no? Therefore, the acceleration vector of B is going to be ax I cap plus ay plus L alpha by 2. L alpha by 2 is 3g by 2 j cap. That's going to be the acceleration vector of B. Sounds all right? Chalo, this much for today. Not very fair. Problem 9, for example, of the sheet. Which is about an arrangement of this kind with a plank resting over it, a rough plank of mass small m. This is a rough plank of mass small m placed on a rough hollow cylinder. This is a hollow cylinder. The cylinder is of mass m, and let's assume it's of radius r. The cylinder is of hollow cylinder, mass m and radius r, right? And a constant force F is applied, and say these are the points of contact A and B. A constant force F is applied, making an angle theta with the horizontal. Assume no slipping anywhere. Find the acceleration of the cylinder and the frictional force at A and B, right? It's a very easy problem, direct application of ideas that you've learned. So, first things first, the free body diagram of the cylinder, say at A, the frictional force is Fa. At B, the frictional force is Fb. What's the nature of Fa and Fb, first of all? Static. Why? Because no slipping at A or B. So Fa and Fb are static. I can't be sure of these directions, and you don't have to be sure of these directions. The solution of the algebra will tell you the directions, right? Okay. Consequently, there is an acceleration of the center of mass A, right? And about the center of mass of this, Fb exerts a clockwise torque and Fa exerts an anti-clockwise torque. So there is a torque, let's say a net torque, which produces an alpha like this, right? Now if I have to look at the acceleration of A, because of pure translation, it will have an acceleration A to the right. Imagine it to be in a state of pure rotation with angular acceleration alpha. It will have a tangential acceleration r alpha to the left. And if there is no slipping at A, the net acceleration of A must be 0. A must be equal to r alpha, right? So this A is r alpha for sure, right? Now, if you look at the topmost point B, because of pure translation, it will have A like this. Imagine it to be in a state of pure rotation about the center of mass. It will have a R alpha like this. But R alpha is A. But R alpha is A. So the acceleration of the topmost point is 2A. We have seen these things earlier too. Now, the point B is in contact with the plank. And there is no slipping between B and the plank. And therefore, the acceleration of B to the right must be equal to the acceleration of the plank to the right. And the acceleration of B that we have obtained is 2A. So the acceleration of the plank must be 2A. Yes or no? Now, so this is the, of course, you know, there is mg and n, also there is normal reaction at B, normal reaction at A. But since it's not important, I'm not representing the normal reactions, right? Now, the Planck side of the story, is there is an f cos theta, which is relevant. I'm not putting up f sin theta, okay? And if the Planck exerts on the hollow cylinder or FB to the right, the hollow cylinder will exert on the Planck an FB to the left. So there is an FB to the left acting on the Planck. Bless you. The mass of the Planck is given to be how much? Small m? Okay. And the acceleration of the Planck is 2a. So what's the equation of motion of the Planck? F cos theta minus Fb must be small m into 2a. The acceleration of the Planck is 2a, right? So we have the Planck side of the story, F cos theta minus Fb must be small m into 2a. We are done with the Planck. Now we don't have to bother our heads on the Planck anymore. Now, the equation of motion for the cylinder. See, for alpha, I could have taken torque about the center of mass, or I could have also taken torque about A, because A serves as the instantaneous center. This is like the pivot for the cylinder. So I could have taken tau equal to I alpha about this. Now so which one would you prefer? So if I took torque about the center of mass, what would it be? Fb into R minus Fa into R. That's a net clockwise torque about the center of mass. That must be I about the center of mass. For a hollow cylinder, I about the center of mass is mr squared. For a solid cylinder, it would have been half mr squared, but for a hollow uniform cylinder, it is mr squared. So that's mr squared into alpha, right? That's obtained by taking torque about the center of mass, writing the equation tau equal to I alpha about the center of mass, right? And the equation of translation would have been what? Fb plus Fa is capital M into A, right? Into A. Now, you don't have a substitute for this, but there is a substitute for this. I could have taken torque about A. So either I use this equation, or I could have even taken torque about A, the point of contact, right? So if I took torque about A, then Fa goes into oblivion. So I have Fb into 2R, I mean, either this or this, any one of them would suffice, right? Not this and this, either this or this would be fine. Fb into 2R is the torque about A, clockwise torque. That must be I about A. What's I about A for the cylinder? Hollow cylinder. Mr squared plus mr squared, 2mr squared. For a hollow cylinder, I about the Cm is mr squared. From parallel axis theorem, add another mr squared, so 2mr squared, right? So Fb into 2R is m 2m into r squared, mr squared plus mr squared into angular acceleration alpha. Yes or no? Right? And very clearly, you know, this 2r, this 2 gets cancelled. R alpha is the acceleration. So Fb becomes ma, because this R alpha can be written as acceleration of the center of mass, condition for pure rolling, right? Now, if FB is capital M into A, FA is very clearly 0. FA is very clearly 0. Or I could have solved using FB and FA right from here. Because see, this will turn out to be R alpha. This is capital M into A. So if FB minus FA is MA and FB plus FA is MA, if I solve these two, 2FB is 2MA, or FA is 0. FA is 0 very clearly. Right? So either use this, or use this and this. Right? So FA turns out to be 0. FA, are you all okay with this? This M is capital M. FA turns out to be 0. Now all that you need to do is, in this FB you can plug in capital M into A. This FB can be written as capital M into A in the equation for the Planck, and then A is readily obtained. So take recourse to this. You have F cos theta minus FB. FB is capital M into A equals 2M into A, giving us acceleration equal to acceleration of the center of mass of the cylinder as F cos theta by capital M plus 2M. Now if A is known, then FB is known. Everything is known to us. Alpha would be A by R, angular acceleration. Is there anything else that we need in this problem? No?
Sir, there can we take tau above B?
No. See, it is not rolling about B. It is rolling about A. There is no slipping here, but it is not rolling about B. Please understand this. There is no slipping at B, but it's not rolling about B. It's rolling only about A. So you can't take torque about A. Yes, because there is no rubbing between the cylinder and the Planck. So FB has to be static. There is no relative motion between the Planck and the point B. So the nature of friction at B has to be static. Got me? So there is a collapsed rubber band. This is a collapsed rubber band. A rubber band in a collapsed state fixed at O, and at this end P there is a mass M attached. There is a mass M attached. This mass M is given to be 500 grams. And the whole arrangement resting on a horizontal surface. And the distance of P from O, is given to be 400 mm. This is 0.4 meters. OP is given to be 0.4 meters. And there is a fixed pin at O. The block is attached to pin O by an elastic cord. This is an elastic cord, a rubber band. See, the difference between an elastic cord and a spring is, see, the spring doesn't have a collapse state. When compressed as well as elongated, it will exert forces. The rubber band in its collapse state will not exert forces, but in its elongated state, it will behave like a spring. In its collapse state, it's pointless to deal with it in the sense that it has no impact, right? But in an elongated state, it behaves like a spring. That's the only difference. So in a collapse state, it exerts no forces. Huh? I mean, initially when there are no forces, anyways it's non-impulsive. It doesn't even know whatever is transpiring, right? But yes, when elongated, then also since it behaves like a spring in an elongated state. Okay. And there is an undeformed length. You know, if you had to straighten this rubber cord, it has a length which is 900 mm, right? Since it's collapsed, it's crumpled within 0.4 meters, but its actual length, when you straighten this cord up, its actual length is 0.9 meters. That's given. L is 0.9 meters. The force constant. So when in an elongated state, No, that's okay. So now, when so after it acquires its natural length and starts to elongate, since it behaves like a spring from that point onwards, there is going to be a spring constant associated with it, and that spring constant subsequently in its elongated state is given to be 100 Newton per meter. 100 Newton per meter. That's given. Now, this block M is set in motion like this. This block M is set in motion like this. The speed in the beginning, for which the distance from O to the block will reach a maximum value of 1.2 meters. Oh, so what's given is L max, maximum length is 1.2 meters for the cord. The speed when, okay. So this is given a velocity v like this. What would happen to the mass m? It will continue to move in a straight line, and the cord will straighten up more and more. After a while, the mass comes to this point P prime, and the cord would have reached its natural length. The cord would have reached its natural length, which is given to be 0.9 meters. Now, while it came to this point, what happened to its velocity? It did not change. It remained v. It remained v. Right? Now things start to happen. From this point onwards, things will start to shape. What is this velocity doing? This velocity has a component along the cord and has a component perpendicular to the cord. This has a parallel component, has a perpendicular component, isn't it? Right? The parallel component would elongate the cord, whereas the perpendicular component would cause the point P to move in a circular trajectory. Had it been only for V perpendicular, it would have moved in a circular trajectory. But now it's a combined effect. There is a radial movement of the point P, and this is the radial movement of the point P, and this is a perpendicular movement of the point P. Yes or no? Because until then, there are no forces in the spring, in the cord, so it will not even experience that, right? At this point, this velocity seems to stretch the cord. Until this point, the cord was crumpled, so it was only opening up, and it did not feel the heat of this parallel component. But this point onwards, it starts to get stretched beyond its natural length. So the cord forces, the spring forces, so to say, start to develop from this point only, right? Only reason I'm not saying anything is because, in any case, the spring will start to elongate from this point onwards. The spring, therefore, will exert on the particle at P a force towards O, which will start to kill this parallel component, but until the time this parallel component gets killed, the rubber band, the rubber cord will keep getting elongated, and there is built up of more and more spring force directed towards O. Yes or no? So there is retardation in the radial direction. The retardation in the radial direction grows in magnitude because the length of this grows, so the retarding force, which is k times change in length, will also grow, right? So eventually this would get completely killed in a little while. The radial component, the component whose line of action passes through O, will get completely killed. Now, but until that point, the length of the cord will keep getting more and more. The cord will keep getting elongated. Right? You know what I'm saying? After a while, at this point, the parallel component becomes 0. The parallel component becomes 0 at P double prime. And there is remain of a perpendicular component, call it say V1. V1 becomes the perpendicular component, right? But until this point, the length of the cord keeps growing. Now after this, what happens? Since this velocity is 0, this length will start to, no, it will not remain V1 always. There is this force in this direction. The length of this will go on decreasing. That means this is the point where the length attains its maximum value. This is the point where the length of the cord attains its maximum value, when the radial component becomes 0, right? And this length is given to be 1.2 meters. This length is given to be L1, say, is 1.2 meters, right? The change in length up to this point is 0.3 meters. Yes or no? Because this is the natural length. Over and above the natural length, there are 0.3 meters available here. So delta L here is 0.3 meters. Right? Yes or no? Now, look, no matter what, the only force acting on the particle is radial. Whichever position you take for the particle, either there is no force, up to this point there is no force. From this point onwards, a force begins to develop, but that force is always directed towards O, and therefore will never produce any torque about O. The force acting on the particle at various positions P, P prime, P double prime has its line of action always passing through O, irrespective of the magnitude, and therefore that force will produce no torque about O. If it produces no torque about O, the angular momentum of the particle about O will remain preserved. The angular momentum of the particle about O will remain preserved. No? So then, what's the angular momentum of the particle in the initial state about O? mv into 0.4? mv into 0.4, yes or no? And in a state of maximum elongation, this V1 would be perpendicular to the cord, so that's going to be mv1 into 1.2, right? Which would mean that V will be 3 times V1. V would be 3 times V1. How about it? Right? Now, all conservative forces, so the total energy of the system will remain constant. What energy did we start with? Half mv squared. Where all did it go? Half mv1 squared plus spring energy, which would be half k delta L squared. Half k delta L squared. What is it that we are trying to compute? V? V is what we are trying to compute. You might want to replace this V1 by V by 3. Replace this V1 by V by 3. Delta is, L is known, K is known, and you will be able to solve for V. Yes or no? V1 is V by 3. So V1 is V by 3. So half m V squared into 1 minus 1 by 9. So 8 by 9 is half of K, which is 100, right? Into delta L, which is 0.3 squared. Plug in the values ms 0.5, etc., and solve for V. When you take the square root, it will be simple because 10 into 0.3, etc. And then this will be 3, this will be 4, so 2, etc. Simple calculations, really. Right? Now, what is the radius of curvature of the trajectory when the particle comes through P double prime? Yes. See, this is the component perpendicular, and the particle is subject to a force k times delta L in the state, right? K times delta L in the state. What does this k times delta L do to the particle? It provides the required centripetal force. So k times delta L is instrumental in providing the particle the required centripetal force. The centripetal force requirement here is mv1 squared divided by the radius of curvature at this point, r. K times delta L, the elastic force in the cord, provides the required centripetal force mv1 squared by r. V is known, so v1 is known, v1 is v by 3, etc., which you can plug into this and solve for r, the radius of curvature. Don't think that the radius of curvature is 1.2 meters. No. The spring force is k times delta L, which gives the centripetal force mv1 squared by r here. Okay, I thought I may have said this earlier, but I'll repeat that. I'll quickly repeat the radius of. Can I wipe this off and quickly tell you what radius of curvature is? Wipe it off? All's clear? So, see, if this is a trajectory, any trajectory, if this is any trajectory for a particle, then the velocity at any point would be along the tangent to the trajectory. Now, at every point, this trajectory could be looked upon as a circle, and the circle will have a certain radius. So when the particle is here, then I can imagine that this is the instantaneous circle which it is negotiating. And this circle has a radius r at this point. With every point of this trajectory, I could associate a circle. Now, if someone gave you, if we had knowledge of the forces acting on the particle, suppose F was the force acting on the particle when the particle was at P, and say this angle theta was known, then F cos theta is the centripetal force which it would provide, and that would be mv squared by the radius of curvature at this point. What would F sin theta do? F sin theta would increase the tangential velocity, whereas F cos theta will provide the required centripetal force. F sin theta would accelerate V. Got me? Thirteen. So there is presumably a very long plank, capital M, resting on a smooth surface. There is a spherical ball of mass small m, spherical ball of mass small m, which descends with a velocity v naught initially before the impact and has an angular velocity omega naught, as shown. Now, the impact did the following. What is given is, because of the impact, the following happened. The vertical velocity reversed in direction and maintained the magnitude, became v naught. That's given. And omega became 0. Omega became 0. That's also given. We'll understand the physics of this. Omega became 0. Okay. Let's first take a look at this. See, when it hits the plank like this, it will exert on the plank a vertical impulse. The plank will exert on the ball an upward impulse, equal and opposite upward impulse, right? So if I look at the ball side of the story, there is an upward impulse jy. There is an upward impulse jy, And what has this JY done? It has changed linear momentum in the upward direction. That means the Planck exerted on the ball an upward impulse JY, which is final linear momentum of the ball in the upward direction minus initial linear momentum of the ball in the upward direction, which is what? M V naught, final linear momentum in the upward direction, minus what's the initial linear momentum in the upward direction? Minus M V naught. So JY must have been 2M V naught. Yes or no? Right? Now, this point, because of this omega, has a velocity like this, right? And the Planck will exert a frictional force on it in this direction, which is a horizontal impulse, which is a horizontal impulse. So there is a horizontal impulse which the Planck exerts. There is a horizontal impulse which the Planck exerts on the ball in this direction, which would be mu times the, this is like the normal reaction, then the frictional force would be mu times the normal reaction. So the horizontal impulse would be mu times the vertical impulse. Yes or no? So this Gx would be mu times the vertical impulse Jy. Right? It acts not from here, say, to be precise, Jx mu times Jy, which is like frictional force acting like this. That's a frictional impulse, impulse of friction, which is mu times the normal impulse. Now, what has this normal impulse done? What has this horizontal impulse done? It has developed on this a velocity v1 like this. Impulse in this direction would be change in linear momentum in this direction. So this mu times Jy would be small m into v1. Would be small m into v1, yes or no? Right? Now, what has killed omega? See, omega was originally like this. This impulse produced this linear impulse. If what is the radius? Small r. This impulse produced an angular impulse about the center of mass, opposing this omega naught, and therefore it killed that omega naught. See, this Jx about the center of mass produced an angular impulse like this, opposing omega naught, and therefore killing omega naught, right? So anti-clockwise angular impulse is what? Jx into a, Jx into a angular impulse, Jx into a is the opposing angular impulse. What has that done? Final angular momentum in this sense minus initial angular momentum in this sense about the center of mass. Final angular momentum in this sense is 0 about the center of mass, because this comes to rest. So final angular momentum about the center of mass is 0 minus initial angular momentum about the center of mass in this sense is going to be minus ICM omega naught. Yes or no? Right? Hey, but this Jx could be written as m into v1, right? So this Jx I write as mv1 into a, where v1 is the horizontal velocity that this develops. mv1 into a is ICM, which is 2/5 ms squared, 2/5 ms squared for a sphere, into omega naught. v1, therefore, the horizontal velocity then turns out to be 2/5 ma omega naught, 2/5 a omega naught. Yes or no? Now, the sphere has mass small m, the Planck has mass capital M. Horizontally, on a system that comprises the sphere plus the Planck, is there any force acting? No. The Planck will exert a frictional force on the sphere like this. The sphere in turn will exert on the Planck a frictional force in the opposite direction. But the sphere plus Planck, there are no horizontal forces acting. That means the linear momentum must remain conserved. What was the linear momentum before the impact horizontally? 0. What would be the linear momentum after the impact? 0. So the Planck In order that it could counter the horizontal linear momentum of the ball to the right, will develop a velocity v2 to the left, such that mv2 must be equal to small m v1. v1 is known, so v2 is also known to us now. v2 then would be small m v1 by capital M. Right? Yes or no? Now, so far so good. What would be the nature of motion of the center of mass of this now? Projectile. Projectile motion is what it would take up, Vx and Vy, right? Vx will remain unaltered, Vy will be opposed by gravity and will become zero at the highest point of the trajectory of this, right? Now, so far so good, right? No issues with this? See, following this impact, the wedge continues to move with a velocity v2 like this, and this takes up a parabolic trajectory. The particle mass m eventually, you know, this is almost on the ground. It's almost on the ground. It falls back to the ground. That means to the state of the plank. It has an initial vertical velocity v0, so it comes back to this in a time which is 2v0 by g, total time of flight. Twice the initial vertical velocity by g is the total time of flight for a projectile. So this projectile, you know, it comes back to the plank in a time equal to 2v0 by g, right? In this time, this is where it was. In this time, this horizontal displacement of the, that means the range of this projectile would have been what? v1 into t would be the range of this projectile, right? Whereas this point, say p, has moved, p on the plank would have moved with the velocity v2 to the left, would have moved. So the point p comes to p prime in the same time, and it would have traversed a distance v2 into t to the left. So then the distance between these 2 points, which is what is being sought here, would be v1 plus v2 into t, this distance, right? So the required distance would be v1 plus v2 into t, where t is 2v0 by g, and v1 so if I take v1 plus v2, so if I took v1 common, so 1 plus small m by capital M into t, which is 2v0 by g, and v1 you can plug in as 2/5 a omega, 2/5 v1 you can plug in as 2/5 a omega. Yes or no? Does the answer match now? Clear? All's good? Let's look at problem number 14. Clear? Can I wipe this off, and have you all settled to this idea? Wipe it off? A uniform rod falls without rotation onto a smooth horizontal plane. At what angle must it fall? Sorry for the great English of this problem. At what angle must it fall rather than must if ball? At what angle must it fall with respect to the horizontal? So, you know, this is falling without rotation. This is the rod AB, and it is falling down. Its center of mass, say, has a velocity v0, and it's in a state of pure translation where every point has a velocity v0. No angular velocity, in a state of pure translation, every point having the same velocity, it falls at an angle theta with the horizontal. We want to be able to find this angle theta. such that after impact with the ground, which is given to be a perfectly elastic impact, it's given to be a perfectly elastic impact with the ground. After impact, it develops an omega, which is the maximum it could be. Develops an omega, which is the maximum it could be. Clear? Okay. Now, see, after impact, what happens? Say, in a very general sense, this is just before impact, and this is just after impact. Just after impact, say, V naught, velocity of the center of mass, becomes V1. Say, velocity of the center of mass becomes V1, and there is a normal force that the ground exerts on this. Therefore, there is an angular impulse exerted on this, because of which it develops an omega. It will also develop, so it gets into a state of general rigid body motion, right? Now, we want to examine the value of theta, for which V1 becomes, for which omega becomes omega max. Since it's a state of perfectly elastic collision, one thing for sure, the total initial kinetic energy is half mv naught squared. Where all does it get delegated? Half m v1 squared plus half of ICM for the rod into omega squared, right? Now, for omega to be omega max, realize V1 must be 0. Omega will be, that means the entire kinetic energy gets converted into kinetic energy of rotation. That's when omega would be omega max. Yes or no? See? In this case, kinetic energy is partially getting delegated into kinetic energy of translation plus kinetic energy of rotation. So, if you want this to, when this becomes the maximum, omega will be omega max. That means when the entire kinetic energy gets converted into kinetic energy of rotation, omega attains its largest value. Yes or no? Right? So, what we are trying to dwell into is, when this becomes 0, that means half m v naught squared equals half of ICM. ICM is 1/12 ml squared into omega squared. This is what we are trying to deal with. This is what, and we want theta which will cause this to happen. We want theta that will cause this to happen. So this gives us V naught equal to L omega by 2 root 3. Right? Now the theta. So far so good, right? So far so good. So V1 becomes 0, life becomes simple. So at this instant, the point A, just after impact, this is just after impact, this is theta, will be in a state, this length is L by 2. L by 2. The point A will be moving, will be in a state of pure rotation, centered at the center of mass, with radius equal to L by 2 and with angular velocity equal to omega. Yes or no? So it will have a velocity which is perpendicular to L by 2 and will be equal to omega into L by 2. V would be R omega. R is L by 2 into omega. It's in a state of pure rotation about the center of mass. The rigid body has gotten into a state of pure rotation. So this is going to be R omega. Right? Now, very clearly, this is theta. This is theta 2. Right? Nature of collision is perfectly elastic, right? So relative velocity of approach must be equal to relative velocity of separation along the common normal. What's the relative velocity of approach? V naught. And that must match up with the relative velocity of separation, which is omega L by 2 cos theta, which is omega L by 2 cos theta, along the common normal. All of this along the common normal. Yes or no? Now, very clearly, I can write this V naught as L omega by 2 root 3. This V naught could be written as L omega by 2 root 3 is omega L by 2 cos theta. Cos theta therefore is 1 by root 3. So the theta would be cos inverse 1 by root 3. Such a theta would produce the greatest omega after a perfectly elastic impact.